All right, starting the recording. So I don't know about you guys, I look at a problem like this and honestly, just all the wording alone is scary. Um, there's just a whole lot of words there, and then I read it and it sounds tough. And honestly, it kind of is. And I would definitely say part C is difficult. But I think we can go through part A and B and go, you know what? Part A and B are not that bad. So this is 2009 B, question 2. And it's a test about developing a test for HIV known as an ELISA test. And this is a little off topic, but Dr. Birx, who's one of the on the coronavirus team, was one of the ones who helped develop the ELISA test for HIV, which I thought was interesting. I didn't know that till I heard it in one of the talks. Anyway, so back to the problem. I'm going to skip the first paragraph because it's just a lot of information. So as a part of a training program, staff at a testing lab applied the ELISA to 500 blood samples known to contain HIV. The ELISA was positive for 489 of those blood samples and negative for the other 11 samples. As part of the same training program, the staff also applied the ELISA to 500 blood samples known to not contain HIV. The ELISA was positive for 37 of those and negative for the 463. Okay, when I read that, I immediately go, you know what? I have two different variables, two different categorical variables. One was a test positive or negative? The other is whether or not the person has or does not have HIV. So the fact that I see two categorical variables, I immediately think I might want to look at a table. And I'm going to show you that a table here, although not required, really is a wonderful organizational tool for this. So when a new blood sample arrives at the lab, it will be tested to determine whether HIV is present. Using the data from the training program, estimate the probability that the ELISA would be positive when it's applied to a blood sample that does not contain HIV. So we have would be positive when applied to a blood sample that does not contain HIV. So in other words, we're saying given that it does not contain HIV, what's the probability it's positive? Well, that right there tells me I'm working with a conditional probability, which means I'm working with the intersection over given. So does not have HIV, that's what I was given, and then I need the probability it's positive, but I'm looking for the intersection between that and does not have HIV. Well, truthfully, that can actually be a little bit overwhelming trying to chase those numbers down from there. So let's look at what would have happened if I would have made a table. If I made a table, they go, well, applied to 500 samples known to have HIV. So right here we have 500 known to have HIV. The ELISA was positive for 489 of those samples and negative for the other 11. So positive for the 489 and negative for the other 11. As part of the same training program, is applied to the ELISA to 500 known not to have HIV. So we have right here, we have 500. Oops. Well, I'm having trouble getting it to pop up. But we have 500 who are known not to have HIV. And in those, it was positive for 37 and negative for the other 463. And so I'm going to go ahead and complete the table. 500 plus 500 is 1,000, and I'll add all my rows across. And everything should add up, and so I have a built-in check. Well, when I look at this, we know that 500 don't have HIV, but it tested positive 37. So 37 over 500 is 0.074. And that one wasn't too bad, but that would get you right there 1 point just because you got that answer. Now, I want to say something about that. let's just say you're all excited because you've read this really long problem and you go, you know what, this is complicated, but I know it's 0.074. And so you write 0.074, and that's all you write. You're only going to get partial credit. If you'd shown the fraction and had just stopped there, you would have received full credit. So you need to show how you got the 0.074, or you could have just left it as a fraction 37 over 500. So real important to show some sort of work, even though it's really simple. Now, you're probably going, Mr. Spencer, did I have to show all that up at the top? No, that was for your educational growth because Ms. Lamb and I, we care. All right? So they pay us to say that, but they don't pay us to be sincere, so I don't really try. Among the blood samples examined in the training program that provided positive ELISA results for HIV, what proportion actually contained HIV? So of those that are positive, so we know we're working with the positive, so I'm looking at this row of positives. What proportion actually contained HIV? So I'm looking for this intersection. So in this case, it's going to be 489 over 526, which is 0.9297. And some of you are going, one, did I have to show the intersection over given? No, you didn't. This part right here, once again, was for your education. It wasn't required. So if you didn't show that, not required. You didn't have. You did have to show. You did have to show the fraction, or you should have shown the fraction. Okay. So you should have shown the fraction. I don't think it actually was required for this part, but you should have shown the fraction. And then there's the decimal percentage, which was not required. All right, so that's part A and B. If you only got part A and B, and I'm trying to say this is an encouragement, if you only got part A and B right, you're going to get a 2 out of 4 points. And the good thing about getting 2 out of 4 points, if you get full credit on the next question, then you would have a 4 out of 2. 4 plus 2 is 6. 6 out of 8 is 75%. 75% is a 5 on the exam. So please remember, don't just stress because there's a part of a problem you're not sure about. And always try to do your best to get some partial if you can, but at the very least, just don't sit there and stress and worry too much about if you miss a part. Just do the best you can because, quite frankly, you don't have to be perfect in order to get that 5. All right? So part C. When a blood sample yields a positive ELISA test, 2 more ELISAs are performed on the same blood sample. If at least one of the two additional is positive, and here's that phrase at least one of the two is positive, the blood sample is subjected to a more expensive and more accurate test to make a definitive determination of whether HIV is present in the sample. Repeated ELISA tests on the same are generally assumed to be independent. This is important because it tells me that I can multiply probabilities. Because they're independent, I can multiply them. Multiplication will applies. So under the assumption of independence, what is the probability a new blood sample that comes into the lab will be subject to the more expensive test that if that sample does not contain HIV? So first off, in order for it to be subject to the more expensive test, the very first thing it does is it has to show up positive the first time. And if it shows up positive the first time, then it gets subject to 2 more tests. And if the first one or the second one of those 2 tests is positive, then it's sent on to the lab. So I basically need to determine, well, what's the probability that it shows up in the lab positive? Well, guess what? The probability that I have a positive test, the initial test is positive, and it didn't have HIV, we did in part A. So the probability of initial is positive is just 0.074. All right, then I'm going to run a second test. Well, if that second test is positive, then I'm going to send it on. So that's 0.074 times 0.074. But remember, if it shows up positive, we're subjecting it to 2 more tests. So it could be subjected to a total of 3 tests before it's sent on. So the first one's positive and the second one is positive. That's right there. But what happens if the first one is positive, then the second one is negative, then the third one is positive? Well, that's still two positives, so it gets sent on. So the probability the first one is positive is 0.074. Then the probability the second one is negative is 1 minus 0.074 or 0.926. But then the third one must be positive, and that gives me 0.074. I multiply those three together and I sum this row and this row together, and I get 0.0105. That's one way to work through the problem. This over here was supposed to be explanation. I hope it helps out a little bit, but not required. If you just showed this work right here, the 0.074 times 0.074 plus 0.074 times 1 minus 0.074 times 0.074, that gets you full credit. That's not the only way to work the problem. Okay, that's not the only way to work the problem. The other way to work the problem is sit there and go, you know what? I need the first test to be negative. I mean, first test to be positive. That's still that 0.074 that we talked about. Remember when I highlighted at least one? That at least should make you sit there and go, oh, that's 1 minus. Well, I need to have one or two that are positive. So I want the 1 minus the probability both are negative. Well, what's the probability of negative? 0.926. So my first is positive. That's the 0.074 from part A. Then I have 1 minus the probability of a negative followed by a negative. And once again, I get the same answer. I recognize part C is very, very difficult. Truthfully, they had a little bit of leeway on that as far as whether or not you got a partial. So if you indicated something along the lines, a probability the initial is positive, and then at least one of the next two are positive, if you have something along those lines and have some sort of mathematical justification, even if it were an error, but it were close, you might have received a partial. Kind of depended. There's a range of things, and they weren't really good at giving us what that range is. And I recognize that part C is quite challenging. Okay, at this point, I'm going to, I thought I was going to stop the share.
You did.
Okay.